Hey, welcome back to Fat Mama Physics! In this video, we are going to go over more examples on impulse. I have a question for you. Was there ever a time when you played a sport and your coach told you to follow through with your shots? If you don't know what I'm talking about, here's a quick example of, say if you play basketball, but any sport, really.
As I release, my hand comes straight over so that the ball are leaving my last two fingers.
Since I coach badminton, here is a quick video of me demonstrating what that means.
No gym during COVID, but notice that my racket stayed in contact with my shuttle as long as possible.
So notice that what the follow-through does is your hand or whatever you're using to apply a force on your ball or whatever object is following that object as you are releasing it. So my question for you is, why would you ever do that? Why would you want to do that in sports? My hint for you is, of course, our impulse equation, change in momentum, equals the force, average force, times the change in time. Give you a moment to think about why do you follow through. And if you're thinking that if I follow through with my shots, if I apply, say, some amount of force on my object, and if I follow through with my shots, I get to increase the amount of time that my force acts on my object, you're onto something. And if that is the case, your change in momentum is going to be greater. Your object is going to gain a larger velocity by the end of which the force was applied. So that, folks, is why you follow through with your shots. Now for some examples. Example 3, Luigi pitches a 150-gram baseball by drawing his arm all the way behind his back. Okay, so that's a good technique, I guess it is. He applies a force of 5.4 newtons, I'm assuming that's the average force, for 0.33 seconds, that's our time, on a baseball starting from rest. So initial velocity is 0. We want to calculate the impulse on the baseball. Whenever we want to calculate impulse, we can calculate it using change in momentum, or we can calculate it using the force times the change in time, or the time the force was being applied. Now, it doesn't seem like we know the change in momentum, because right now we don't know what the final velocity is. But we do know what the force is. We do know the time. So we're going to use force times time to calculate impulse. And substituting 5.4 newtons for the force and the 0.33 seconds for the time, we can put that into our calculator to find out what that is, giving us 1.782. and units of Newton second. And of course, we need to round it to 2 sig figs, so that's going to be 1.8 Newton seconds. And it doesn't seem like there is a direction in this question. So we can just leave this value as a positive value, and that's if sufficient, okay? So that's how you would calculate impulse. B, the final velocity of the baseball. Okay, so now we have the impulse. We can go ahead to calculate the final velocity from change in momentum. So what does that look like? I have change in momentum equals the force times the time in which this was impulse, and we calculated just that. But now we want the final velocity. So to write this out, we have the mass times the change in velocity, which is going to be final velocity minus initial velocity. And if I continue to write this out, I get mass times final velocity minus mass times initial velocity. But hey, initial velocity is 0. We love things that become 0. So let's make that go to 0. So all we are left with is force times time is equal to the final momentum. And to get that final velocity, we just need to divide both sides by our mass in order to do that. And then we get the velocity is equal to force times time divided by the mass. All we need to do now is to plug in our values, and we are good to calculate. So putting this in, I get 5.4 newtons times the 0.33 seconds for the time. I could have just used impulse, and all of that divided by the mass of the baseball. But wait, the mass of the baseball is in grams. So we need to divide this by 1,000 because there's 1,000 grams in 1 kilogram to get kilograms. Moving decimal 3 times, 1, 2, 3, 0.150 kilograms. So then putting that in and into our calculator, we get 11.88, which then that's going to round to 12 meters per second. There is no directions included in the question, so I'm just going to leave that as a positive value, and that is sufficient. Not bad, eh? Okay, so that's our startup question. Now, to illustrate the follow-through effect, we look at example 4. This time, Luigi was forced to pitch, well, woohoo, same baseball, but he is standing up against a wall where he could only apply a constant force of 54 newtons over, oh, hey, look, it's a shorter time, over 0.15 seconds. If the baseball started from rest, oh, again, initial velocity is 0, calculate the impulse on the baseball, and again, the final velocity of the baseball. So if you're not sure what I am talking about when Luigi is up against a wall, imagine there's a wall, and imagine I got Luigi. If he were to throw this baseball, his hand would start at the wall. He can't extend it all the way behind the wall. That's not possible. So starting from here, his release would be somewhere over here if he's lucky. So there's a shorter time in which he applies that same force. But, so then that will maybe, perhaps, reduce the change in momentum of our baseball. But that's for you to figure out. So this is a good time for you to pause the video and try example 4. Good luck! And I will do the solutions on Fast Play.
So the impulse that he exerts is either to change your momentum, or if you have the force times time, that works as well, and that's exactly what we have. So the force times our time gives us 0.81 newton seconds. Now for the final velocity of the baseball, we need the change momentum equals ft, and since we have the initial velocity is 0, we can just divide both sides by mass, and giving us a total of 5.4 meters per second.
And here are the solutions. So notice that with a shorter amount of time, not a lot of impulse, leading to a lower change in momentum, and at the end, dividing by the mass, we get a lower velocity. So 5.4 meters versus 12 meters per second. Sorry, I meant meters per second. So that is the difference between a follow-through and a lack of a follow-through. So hopefully you learned something in this video about impulse and which you can apply to your practices. I wish you good luck. Thank you for watching this video, and Fat Mama Physics signing out.